years old in C in 1999, and now he works at the University of Lyon. Today he will speak on some recent developments in the theory of building.
Thank you very much. I thank the organizer and the panel committee for the invitation. I feel very, very honored. Okay, so what is the general theme of my talk? In some sense, it's to explain how to do geometric group theory controlled by Lie theory. By this, I mean that geometric group theory is a way to study discrete groups by means of isometric actions on nice metric spaces. And Lie's theory, as we all know, is a more structured domain of mathematics with a lot of examples. And what makes this interplay possible, I think, at least at some point, is the notion of a building, which is a very specific kind of cell complexes. So let me first give a rough summary of the content of this talk. So buildings will be the main object of study. There are cell complexes which have lots of symmetries, so that many groups have interesting, highly transitive actions on them. And to relate this notion with what I've just said, I would like you to have in mind the fact that there are two extreme situations in some sense. One which I call the classical, which deals with groups which are very strongly controlled by Lie theory, because typically there are algebraic groups over local fields. And the other extreme situation is what I call here non-exotic situation, in which the buildings will not be relevant at all from any theory coming from algebraic groups. So I will define, the first thing I will do concretely is to define buildings, of course. But first, a first approximation to this notion is an analogy between buildings and Riemannian symmetric spaces of non-compact type. Typically, again, it's there will be groups. Buildings will be spaces with completeness and non-positive curvature properties. What we will lose is the smoothness. These spaces are not at all relevant to differential geometry. We will lose, in some sense, homogeneity, but still we will have compact fundamental domains for good groups. But at least, even if we lose smoothness and homogeneity, there will be an interesting buildings can be seen as interesting generalizations of symmetric spaces. Okay, so this talk will be shared between the analogy part, which tells you that you should see a building as a generalization of a symmetric space, and kind of opportunity in the exotic case, in the case of non-Euclidean buildings, the opportunity to have new phenomena in group theory. So. Okay, and the point is to see where the border is between analogies and new phenomena. Okay, so here's the plan. I will define buildings first, of course, and give some situations, some examples. And then the second part will be the classical one. It will be dealing with Breathitt buildings. So the point is, if you want to say something new in this well-established theory, you have to use sophisticated tools, and I will very quickly explain how to use analytic geometry in the sense of Berkovich to compactify Breathitt buildings. And the last part is the part where the situation is wider in some sense, in the sense that you have a less good Lie theoretic control on the spaces, but you get new phenomena. Typically, you get the outcome will be a wide family of finitely presented infinite simple groups. Okay, buildings. So buildings are cell complexes, which by definition will be unions of slices, which will be called apartments. And so the first thing I will do is to define these slices. And these slices are modeled on Coxeter complexes. So to fix notation, I recall that Coxeter group is the presentation of a Coxeter group, which prescribes the order of products of canonical generators. This presentation is simply encoded by a symmetric matrix. So since I want to do geometry as soon as possible, I attach a geometry to this Coxeter system, as is well explained in Bourbaki, for instance, which is the Coxeter complex of the Coxeter group. So this is abstractly a poset, which is very simply defined in the sense that you look at all the translates by elements of W of the groups, of the subgroups generated by subsets in the canonical generating set. So it's not very illuminating this way, but these complexes always admit nice metric realizations. But what I suggest for this talk is to go the other way around. Namely, you start with a standard geometry, a Euclidean or real hyperbolic space, and you pick a suitable tile inside. Suitable means that the diagonal angles must be integral submultiples of pi. Why? Because I want to apply Poincaré theorem, which tells you that if you reflect the tile along the codimension 1 faces, then you get a discrete group, which is Coxeter. And the tiling you obtain of the ambient space is a realization of the Coxeter complex. And this is all you need to have in mind for Coxeter complexes. This will be enough. Okay, so a little bit of further additional terminology. When the Coxeter complexes, the Coxeter complexes will be slices, and when they will be Euclidean reflection groups, the building will be called Euclidean. Okay, so let's go to buildings. The definition is due to Titz in the late 50s. So given a Coxeter system as before, a building is a cell complex covered by subcomplexes, which are requested to be all isomorphic to the Coxeter complex, and which will be called apartments. And I request two incidence axioms. The first one is that any two simplices, which will be called facets, any two simplices have to be contained in an apartment, in a suitable copy of the tiling. This is the first incidence axiom, so to speak. And the second complementary one is the fact that given any two apartments, there is a cell isomorphism between them, which fixes the intersection inside the building. Of course, we know that they are isomorphic by definition, but we want them to be precisely isomorphic via an isomorphism which fixes the intersection in the space. Okay, so if I want to sell these axioms more concretely, because they are a bit hard to swallow, assume I want to do a geometric group theory. I want to have a distance on the space. So if I assume that I have a W invariant distance on the Coxeter complex, on each slice, then these axioms enables me to globalize the metric in such a way that it restricts to the initial one on each apartment. Why? Because axiom 1 tells me that whenever I'm given 2 points, I have a candidate for the distance which is computed in some apartment containing them, and up to some additional work, second axiom tells me that the distance is independent from the choice of the apartment. Okay. So typically, dimension 1 example is given by a tree in which all vertices have valency at least 2. So in that case, the Weil group is infinite dihedral. And as I said before, this is an example of a Euclidean building because the Weil groups, the reflection group, is Euclidean. Okay, so let's draw some pictures. Here's the one-dimensional examples with an infinite Weil group. So as I said, the Weil group is the infinite dihedral group. And if I want to draw something which is higher dimensional, then I'm already in trouble in the sense that this tiling, this red tiling, should play the role. It's an arbitrary choice, of course, of a Coxeter tiling. But this tiling should play the role of a geodesic line in the previous case. So now what I have to do to obtain a building is to glue some half tilings along walls in the initial one, and to have sufficiently to iterate the procedure in such a way that the incidence axioms will be eventually satisfied. Okay, so it's a bit a pain to describe more precisely, and actually this is not usually the way you construct buildings. The usual way is to start with a group with nice combinatorics called TIT systems, and you get for free highly transitive action on a building which is completely explicit from the combinatorics. Okay, so let's turn now to the analogy I would like to use. The first, well, not the first, but one well-known application of buildings is Bruatit's theory. Typically, you start with a simple matrix group over some local field. Then you know from this theory that there is a Euclidean building, a well-defined Euclidean building, on which the group acts with a compact fundamental domain. So this is what you can use to get, for groups like SLN-QP, to get some decompositions which are well known in the case of real Lie groups, typically Iwasawa or Cartan decomposition. Okay, so this dates back to the 70s by the first big volume by Bruat and Titz. Now I'm interested in slightly more exotic situations, typically which other building can I produce. And of course, there is one requirement I impose, namely the fact that the new buildings I want to produce must have an interesting group action. Okay, because there is, in the examples I gave, typically the trees, what can be very bad is if I choose a tree in which all the valencies are pairwise distinct. In that case, there is no automorphism at all. And for group theory, the space is not interesting at all. Okay, so the requirement I asked for the new buildings is that they admit interesting group actions, very transitive group actions. Okay, so these buildings do exist. Typically, in the early 90s, people were interested in buildings in which apartments were tiling of real hyperbolic spaces. And well, to support the analogy with simple Lie groups, some buildings were cooked up in such a way that the full automorphism group of the structure was a huge, totally disconnected and countable, abstractly simple group. So this is an encouraging result for group theory, and for discrete, for geometric group theory, for the study of actions of groups on metric spaces, there was an analog of Mosto's strong rigidity in the sense that there is a family of hyperbolic buildings which are characterized by a discrete co-compact action of some countable groups. So this is an example of a singular analog of Mosto's strong rigidity. So this is only a sample of some results available for exotic buildings, but I simply want to conclude this part by the fact that you shall see buildings with infinite Weil group, with infinite apartments, as analog of symmetric spaces, and accordingly, you shall see full automorphism groups or full isometric groups of the buildings as analog as generalizations of simple Lie groups. Okay, and the point will be to what extent this analogy is valid, and if it's no longer valid, what can we get from that? Okay, so now let's turn to the classical part, namely the part of which is in which the interplay with Lie theory is particularly strong. This is typically Bruatit's theory. So here's a kind of a shameful summary of Bruatit's theory, which is much richer, but still. Okay, let's start with a non-Archimedean field and a reductive group over this field. As I said, Bruatit's theory provides Euclidean buildings in this situation, on which the group of rational points acts strongly transitively. So strongly transitively is now a more technical condition, a more precise condition. It says that the group of rational points G of K acts transitively on the inclusions of a chamber in an apartment. Okay, so namely, if I'm given a compact chamber in an apartment and another certain inclusion of a chamber in an apartment, I can always find an element which sends the chamber to the chamber and the apartment to the apartment. Okay. So this is what's going on for symmetric spaces with points in flat subspaces. Okay, the other nice features in Brugatti theory is the fact that the building X carries a complete non-positively curved distance, for which the apartments are the maximal flat subspaces. Okay, so complete is the naive notion of, involving Cauchy sequences. There is no mystery here. And non-positive curvature means that first there is a notion of geodesic segment. Between any two points, there is there's a segment, a continuous segment parameterized by length, which joins, for which the 2 points are, of which the 2 points are the extremities. And non-positive curvature is translated by the fact that the geodesic triangles must be at least as thin as in R2, the Euclidean plane. This is naive, but this is very efficient, actually. Okay, what is nice with these two, actually, whenever you're given a metric space which has enjoys these two properties, you have a nice characterization of a kind of barycenter for any non-empty bounded subset. And this is very useful because if you apply this to orbits by isometric action, then you're given a fixed point lemma. Okay. I do it again. If you have an isometric group action which has a bounded orbit, then the unique barycenter of this bounded orbit will be a fixed point. So in particular, if the isometric group is compact, it has a fixed point. So this applies, as I will explain, this applies to maximal compact subgroups in G of K, but this also applies actually to Galois groups for their profinite, for their cool topology, when you do some descent argument, descent of the ground field. But I won't be talking about this. Still, you use this fixed point lemma to have a kind of dictionary between maximal compact subgroups and vertices in the building. Okay, in one direction, if you start with a compact subgroup, you take the fixed point set. And it turns out that this fixed point set reduces to a vertex, a single vertex. In the other direction, you pass to the stabilizer. Okay. This is the only thing I will need. Of course, Brugatti is richer. This is only half of the theory because the other half would be, I would say, integral structures on the group. Structures, group schemes over evaluation ring, which are actually used also as a tool to prove all these statements, many of these statements. But I won't need them until, say, the end of this part. Okay, so please keep in mind that whenever you're given a vertex, you're given a maximal compact subgroup by taking stabilizer.
And how do you ensure that the barycenter of the object is a vertex?
Is a
Why is it?
No, because, well, typically, well, roughly speaking, the group is maximal for compactness, with respect to compactness. So if you have 2 points, then the vertex stabilizer would be bigger. It's not a proof, it's an intuition. Okay? So, I want to compactify Brugatit's building, Euclidean buildings, because it's useful, for instance, for induction arguments in representation theory, for instance. Okay, so the first compactification procedure that we defined was done with Yves Guivarch, using this beautiful fact that given any locally compact group, the set of closed subgroups has a natural compact topology. This is a bit surprising maybe, but it is true. Typically, the set of closed subgroups, if for instance your group is metrizable, then you can see this topology as the one in which the convergence is given by pointed Hausdorff convergence. Okay, so if we're back to the previous page, we know that we can identify vertices in the buildings and maximal compact subgroups. So via this equivalent identification, I can see the set of vertices in the vertex building as a subset of the compact set of closed subgroups. In other words, the buildings appears in the space of closed subgroups via identification between vertices and maximal compact subgroups. The building, or maybe it's a zero skeleton, is the set of maximal compact subgroups. So the question is, what do I do? So I want to compactify buildings. So there is a naive idea, which consists in closing the set of maximal compact subgroup in the set of closed subgroups. It's a naive idea, but it works. It gives at least an equivalent compactification of the set of vertices. The question is, can I intrinsically characterize the groups I obtain when I close the set of maximal compact subgroups? Okay, I get a set of closed subgroups which is bigger than the set of maximal compact subgroups. And the question is there a common characterizations of the maximal compact subgroups, and so to speak, their degenerations at infinity? And the answer is yes. There is a notion of dynamical flavor, which is distality. Distality tells you a subgroup of G of k is said to be distal if it has no dynamic at all on the Lie algebra, which is true for compact groups, of course. And this is what is kept by taking closure, and it characterizes the set of the closure. The groups you obtain when you close the set of maximal compact subgroups. The other question is that, of course, you have an action of the group G of k by conjugation on its closed subgroups. Again, it's a kind of naive action. You have action by conjugation. The set of closed subgroup is permuted by conjugation by the initial group. Okay, so when I take normalizers, when I take stabilizer for the action of this space, again, same question, do I get an intrinsic characterization of the stabilizers? And the answer is yes. And the answer involves a kind of more useful notion, namely that of amenable subgroup. Okay, so it's also a notion, in some sense, from topological dynamics, which is very useful in rigidity theory. And the advantage of this notion is that it has a lot of equivalent definitions via unitary representations, via fixed point properties. Okay, so up to finite index, the normalizers of the limit groups and of the maximal compact subgroups and of their limit groups is by taking a normalizer, I obtain the geometric parametrizations thanks to the compactification, the group theoretic compactification of the maximal amenable subgroups of the rational points. Okay, so this was extended by proving that the action itself on the boundary of G of k is amenable, and amenability of an action is a useful thing to prove conjectures such as Bohm cone and so on. Okay, so this is a result which has a kind of dynamical flavor, and which has one drawback of this compactification is the fact that I only compactified the zero skeleton of the building. So now I want to fill in the compactification. And in some sense, you feel that you cannot use the set of closed subgroups, the space of closed subgroups, because if you take any 2 points in a given chamber, in the relative interior of a given chamber, you get the same stabilizer, because the group acts by cellular isomorphism. So it's not enough. In some sense, the space of closed subgroup is not big enough to distinguish 2 points in a given open cell. So there is a trick has to be done, and the price to pay is to use analytic geometry over non-Archimedean fields. Okay, so let me very quickly sum up what is Berkovich geometry.
Sorry, but this previous compactification, what generality was working? Vegan buildings or?
Okay, so it was generalized by Capras and Lecureux to arbitrary buildings. Yeah. So there is a notion of analytic geometry over non-Archimedean fields, which mimics in some sense algebraic geometry, but it replaces spectra, prime spectra of unit rings by, so to speak, analytic spectra for Banach algebras. So instead of considering rational points over extensions of the ground field of the K algebra of the unit ring of the K algebra, you consider multiplicative bounded seminorms. So this way you catch all rational points, but you possibly rational points, but you also add more points in such a way that you overcome the difficulty of total disconnectedness of the field. So the nice point is that every algebraic variety over the local ground field has an associated analytic space. The attachment, which goes from K-schemes to key analytic spaces, is a functorial. And there are in the two basic cases of algebraic geometry, in the affine and the projective case, you get expected properties. Typically, if you start with an affine variety, then you can describe explicitly the analytic space attached to it. And if you start with a proper and separated scheme, you get a compact Hausdorff space. And this is all I want to use. You don't need to know more from Berkovich geometry for the next slide. Okay. Actually, the only thing that you need to know is that the attachment is functorial. So whenever you're given an algebraic map, you get a continuous map between analytic spaces. And whenever you're given a proper variety, you get a compact space. Because what I want to do is to embed the building in the analytic space attached to some proper variety, typically a flag variety. Okay, so let's go back to the building situation. So as I said, as I write here, I'm not happy with the fact that I only compactify the zero skeleton of the building. So now here's the result, which is technical, which you can read quickly. The only idea is the following. Whenever I'm given a point, possibly not a vertex, and preferably not a vertex, instead of taking its stabilizer in the set theoretic sense, I consider its stabilizer in the analytic theoretic sense, which means that I consider all the non-Archimedean extensions of the ground field. This enables me to define an analytic subgroup in the sense of this analytic geometry. And since I take into account all the extensions of the ground field K, I can distinguish 2 points in an open cell. This is precisely because I can take into account all the extensions. Okay, so this statement is the most technical one of the talk. If you read the end, you see that it's not what I want. I have an equivariant embedding from X to the analytic space of Gian. So this is bad for two reasons. First, the image is closed. And second, Gian is not compact because it's the analytic space attached to an affine variety. But the idea is to compose this map from X to Gian with the analytic map attached to a fibration to a flag variety. This time the image is no longer closed. The map is still equivariant. So when I close the image of this composed map, I do get an equivariant compactification of the building. And the extra thing is, with respect to the group, the naive group theoretic compactification, is the fact that I can vary the conjugacy classes of parabolic subgroups so that I get the analog of the family of Satake compactifications of Riemannian symmetric spaces. Okay, I have as many compactifications as conjugacy classes of maximal proper parabolic subgroups. So this is a compactification which still deserves to be used, I think, but it's on your project so far. Okay, so this is the end of the analogy part, of the classical part, sorry, which is control, where I have a strong control from Lie theory on this situation of an isometric group action on the space. Now let me turn to the exotic part, the exotic possibilities. And the main objects which are studied in this exotic part are called Kac-Moody groups. Okay, so I have to introduce them quickly. So Kac-Moody groups were constructed by Tits again to generalize algebraic groups, but in some sense the definition for those who like algebraic geometry is disappointing because there is no geometry, there is no structure from algebraic geometry at all on these groups. They are defined by generators and relations in a way which generalizes Steinberg's presentation of SLN or actually of any simply connected split algebraic group. But still they have nice properties which probably were the motivation for Tits. They have a nice combinatorial structure, which is called the Bn pair. So I won't list the axioms of Bn pair because it's completely useless for what I'm interested in, and mostly it is conveniently translated into geometric terms, namely in terms of strongly transitive actions on buildings. So if I go back to my first slides, we shall see Kac-Moody groups as kind of algebraic machinery to produce buildings automatically endowed with a nice, with strongly transitive group actions. Okay, and this time, what I first want to explain is that the buildings we obtain can be, so to speak, kind of wild with respect to Euclidean buildings. So what I need to define a Kac-Moody group is simply a ground field and a generalized Cartan matrix. That is a matrix with 2's on the diagonal, non-positive coefficients, and I simply require that I have a symmetry of vanishing of the coefficients with respect to the diagonal. So what is missing for a true Cartan matrix is the fact that this matrix is not requested to be the product of a diagonal matrix with a scalar product matrix, which would be the killing form. I don't want that. I don't need that. Okay, so the example, the standard example, for instance, in a representation theory of these objects, is in some sense the algebraic loop groups, which are often presented as canonical examples for Kac-Moody groups. You take your favorite simple group over some field, and you evaluate it over the Laurent polynomials. Okay, so this will be typically a Kac-Moody group of a fine type, and I want to spend the rest of my talk by explaining you that for group theory, it's a misleading example. Because typically, this group is finitely generated and linear, so it's residue finite, meaning that the intersection of the finite index normal subgroups is trivial. So for simplicity, one of the most basic properties like simplicity in group theory is very bad. Okay, so what I want to do, but still this group is an arithmetic lattice. So in some sense it's close to simplicity in the sense that it satisfies Margulis' normal subgroup theorem, which tells you that any normal subgroup has finite index. Okay, so the analogy part, if I want to consider a Kac-Moody group, the analogy part tells me that I would like to prove Margulis' normal subgroup theorem, which is half of simplicity in some sense. It rules out infinite quotients. And then I shall stand by decisive differences with respect to this linear case to also rule out the finite quotients. That's the trick. And the point is that it works. Okay, but first I have to support the analogy between a generic Kac-Moody group, an arbitrary Kac-Moody group, not necessarily affine, and an arithmetic group in positive characteristics. Okay, so first I need a geometry to be able to do something, since I have no structure from algebraic geometry. So here is the first basic fact, which is probably one motivation for Tits, which was a motivation for him. Any Kac-Moody group acts on the product of two isomorphic buildings. And the explicit rule to deduce the Weil group from the general Cartan matrix is exactly the same as the one known in classical finite dimensional Lie theory, except that you had the possibility to have an infinite coefficient in the Coxeter matrix. But this is already known in the affine case. So this is the same rule. Okay, but recall that I have much less requirements on the general scatter matrix than for a Carter matrix. So the idea is to lift, so to speak, this rule from A to M, to read it backwards, in order to produce buildings with automatically strongly transitive group actions. Because what I didn't write in this first point is that when you restrict the action of lambda on a single factor, the action is strongly transitive on inclusions of chamber in apartments. Okay. So let's play with this, and again, let's go back to this misleading example, which I will call and so forth affine types. But if you have in mind the pictures I drawn at the beginning, you may also wish to have buildings in which the apartment is given by Fuchsian tessellation, typically a triangle with angles equal to pi over 4, pi over 6, or possibly a right angle argon with at least five edges. And then this is also available. But again, it's a bit, in some sense, the general case is a mixture, because what is a bit, if you only read these two examples, you may think that any apartment lives in a constantly curved spaces. This is unfortunately not the case. But still, here is the first argument to say that Kac-Moody groups over finite fields are analogs of arithmetic groups over function fields. Let's assume that, until the rest of the talk now that the ground field is finite and that the Weyl group is infinite. We introduce the growth series of the Weyl group. Then what we immediately get from the finiteness of the ground field is the fact that the Kac-Moody group will be finitely generated by its very definition, by its presentation. And the other point is that the geometry will be locally finite. The buildings will be locally finite. So in particular, the full automorphism groups of the buildings will be locally compact for the compact open topology, and they will admit Haar measure. They will carry Haar measures. So the next question is, if I want the list I have to get, if I want to compare an arbitrary Kac-Moody group with a lattice, with an arithmetic lattice in the fine case here, is to have to be able to see lambda as a lattice for the geometry. And this is indeed the case. If Q is large enough with respect to the growth of the infinite Weyl group, then lambda is a lattice of the product of the buildings, meaning that it's a discrete subgroup in the isometry groups of the spaces of the buildings. So it's discrete, and the homogeneous space when you obtain when you mod out the isometry groups by the discrete subgroup carries a finite invariant measure whenever Q is large enough. Okay, so this was encouraging. It was proved 15 years ago. And now I can turn to this strategy, which consists in exploiting the analogy to get as many results as I can, and then standing by differences to have new phenomena. So this is what's going on in the simplicity result. Okay. So this is what we obtain with Pierre-Emmanuel Capras. If you start with the Kac-Moody group over a finite field, and if you assume it's a lattice, this is the assumption in the second sentence, then whenever the buildings are not Euclidean, meaning that whenever you avoid the obviously linear case of loop groups, then you get finitely generated simple groups. So there is a sharp dichotomy, which you can read in the geometry of the spaces, of the buildings, between affine arithmetic groups, arithmetic Kac-Moody groups, and simple finitely generated groups. Okay, so this is a reformulation of the theorem. Whenever the group has no matrix interpretation, because you cannot see, it's not affine, it doesn't come from an affine Dynkin diagram, then you get a simple group. an infinite simple finitely generated group. And again, if we want to go to stick to questions from geometric group theory, an improvement with Pierre Emmanuel is the fact that you can even produce, varying the Dynkin diagrams up to proving an additional non-distortion result, you can prove that you get infinitely many quasi-isometric classes of finitely presented simple groups. Okay, so you get finite presentation for infinitely many A's. And you can even assume that among these infinitely many quasi-isometric classes, you have infinitely many classes of Kazhdan groups. Kazhdan property is another property which has, like a miniability, has a lot of equivalent definitions by means of fixed points and unitary representations. And okay, the only notion I haven't defined so far is quasi-isometry. So it's typically a notion from geometric group theory. It's a notion which is due to which was very used by Gromov. It deals with metric spaces, and the notion of quasi-isometry is an equivalence relation between metric spaces at large scale. And in the case, so it's roughly speaking, is by Lipschitz equivalence up to additive constant. And now it is useful for groups because you can see groups as metric spaces via their Cayley graphs. If you take a finite generating set, you have a graph. So the idea is to compare, which doesn't depend up to quasi-isometry on the finite generating set. And the idea is not to classify finitely generated group by up to isomorphism, but up to quasi-isometry, which is a coarser equivalence relation, but more reasonable. Okay, so I would have liked to explain you, to sketch the proof, but I think it's better to mention the fact that there is another possibility to define interesting groups in this Kac-Moody situation, which consists in restricting the action of a Kac-Moody group over a finite field to a single factor, to a single building. Then the action is no longer discrete. There is not enough space for the action to be discrete. You have infinite stabilizer. And the point is to close the stabilizer of a chamber, which becomes infinite, in the full automorphism group of the building. So you get a compact, totally disconnected group. Okay, you get a profinite group, which actually is virtually, up to finite index, a pro-P group, where P is the characteristic of the finite ground field. So this is the analog of kind of Iwauri subgroup in Bruatitz's theory. And what we could prove with Inac-Abdebosk is the fact that well, it's only a starting point. This group is finitely generated as a pro-P group. And actually what I wrote here is computation of the first, the degree 1 homology with coefficient in Z mod P. So this is something that should be improved. And of course the question is again, so now you have a pro-P group, so simplicity doesn't make sense. It's not a good question, but what makes sense is, can we disprove linearity whenever the groups are not affine, or at least when the Dynkin diagram is far enough from classical Dynkin diagrams. Okay, so this is something which we are working on, and okay, I think I should stop here, except for this. Thank you.
So for this large class of very distinct groups, you vary A or you vary Q?
We don't need to vary Q, and actually we don't know if varying Q provides different quasi-isometric classes.
Bourdon does.
Sorry?
Bourdon does, probably. Marc Bourdon, probably.
Ah, yeah, okay, yeah. But it's not the same lattices. The Kac-Moody lattices are not uniform, so. Okay. Yes, please.
Please go to where you define a set of multiplicative bounded seminops.
Sorry?
A set of multiplicative
Yes.
bounded seminops.
Yes.
There's something you define next.
Okay.
Next to the
Yes.
set of multiplicative
Okay.
bounded seminops.
Okay, I don't have my slide anymore. So the set of multiplicative bounded semi-norms in Berkovich geometry plays the role of the prime spectrum in algebraic geometry. Okay. What is bad with the prime spectrum is that you cannot have you cannot avoid total disconnectedness of the local field. So now, if you want something which is locally connected, this is Berkovich, one of Berkovich's stronger ideas. You have to take something which is bigger than the prime spectrum. And the idea is to take this analytic spectrum, this analytically defined spectrum. And you can, okay, the intuition is that it is bigger in the following sense. What is a K point? Well, you're given a K algebra. We take an affine scheme. A is the K algebra of the affine scheme. So the prime spectrum corresponds to maps to fields from A to big K, where K is an extension of small k. Okay? So what Berkovich says is that if you want to have good local connectedness, you have to replace these maps by, so to speak, the compositions from such a map from A to big K, an extension of small k, with the absolute value of big K. This is how you get maps to, this is how you get semi-norms, multiplicative semi-norms. Okay? So this is the idea. And in some sense, you shortcut the step where you go through a field and then you compose this map to a field with the absolute value. You go directly to R plus via a multiplicative semi-norm. So you get, well, since if you see rational points as maps of that kind, you get many, many points. And since you add a lot of points, you get connectivity, at least local connectivity.
Now the next question is, would this be an infinite dimensional space? So how large is it?
Which spaces?
The space we are talking about.
The buildings? No, they are finite dimensional. Actually, they have the dimension is bounded by the cardinality of the index set for the generalized Cartan matrix. Okay.
Any other questions? No, let's thank the speaker again and all the speakers.